In 2021, NASA's engineers faced a nightmare scenario. A critical fault had appeared inside the James Webb Space Telescope, the most complex scientific instrument humanity has ever built. But nobody could touch it. It was already 1 million miles from Earth. So they did something extraordinary. They fixed the problem on a copy. A perfect, living, real-time digital copy of the telescope, running on computers back on the ground. They diagnosed the fault in the copy, simulated the fix in the copy, verified it worked in the copy, and then, and only then, sent the commands to the real telescope 1 million miles away. It worked flawlessly. That copy has a name, and it's about to transform every major industry on this planet. It's called a digital twin. What if I told you that right now, today, your city exists in two places simultaneously? That a jet engine flying 35,000 feet above your head has an identical twin living inside a computer, tracking its every heartbeat in real time? That a surgeon may have already operated on your heart, virtually? And that scientists are building a full digital copy of our entire planet, atmosphere, oceans, ice sheets, weather systems, all of it, inside a supercomputer? Digital twins are one of the most consequential technologies of the 21st century, and yet most people have never heard the term. By the end of this video, you'll understand why Boeing, Airbus, NASA, and Siemens are collectively investing billions of dollars into this technology, and why it may already be quietly saving your life without you knowing it. But to understand where we're going, we need to start where this idea actually began. Not in 2025, not in 2002, but in 1970, with 3 astronauts, a crippled spacecraft, and a room full of engineers who had 4 days to think of something fast. April 13, 1970, Apollo 13. Astronauts Jim Lovell, Jack Swigert, and Fred Hayes are 200,000 miles from Earth when an oxygen tank in the service module ruptures. The lunar landing is immediately scrubbed. 3 human beings are now drifting through space with a vessel with failing power, failing oxygen, and no obvious path home. In Houston, engineers scramble. And here's the critical thing they do. They go to the physical replicas, exact copies of the spacecraft systems sitting right there in the building. They can test procedures on the copy that would be too dangerous or impossible to test on the real ship with 3 people aboard it. They experiment, they fail, they iterate, they find a solution. Those physical replicas saved 3 lives, and they planted a seed. Fast forward to 2002. A NASA engineer and product lifecycle management researcher named Michael Grieves gives a presentation that will quietly change the world. He describes a concept he calls the digital twin. The idea is almost radical in its simplicity. Every physical product should have a complete virtual counterpart, not a static blueprint, not a snapshot, but a living, continuously updated digital model, connected to the physical object by a constant stream of real data. Always current, always accurate.
At the time, this was largely theoretical. The sensor technology wasn't quite there. The computing power wasn't quite there. The internet infrastructure wasn't quite there. Then came the Internet of Things. Then came cloud computing. Then came artificial intelligence. And suddenly, everything Grieves described became not just possible, but routine. Today, the digital twin market is worth $24 billion. By 2032, analysts project it will exceed $259 billion. That's not a niche technology trend. That's a fundamental shift in how human civilization manages physical reality. Let's get precise about what a digital twin actually is, because the term gets thrown around loosely, and the details matter. A digital twin has 3 core components. First, the physical object. It could be anything: a single bolt, a gas turbine, a hospital building, an entire river delta. Embedded throughout that object are sensors, hundreds, sometimes thousands of them, measuring temperature, pressure, vibration, humidity, electrical current, every single second. Second, the virtual model. This isn't just a pretty 3D render, it's a physics-based computational model that actually simulates how the physical object behaves, how it flexes under load, how it heats up, how its components age and wear over time. The model is continuously updated by the sensor data, staying in perfect sync with the physical world. Third, the feedback loop. This is where it stops being a monitoring tool and becomes something genuinely transformative. Powered by artificial intelligence and machine learning algorithms, the digital twin analyzes the incoming data against simulations of thousands of possible future scenarios. It answers questions that would be completely impossible to answer any other way. Questions like, given this vibration pattern in bearing number 7, how many more operating cycles before it fails? If I run this production line at 105% capacity for 2 weeks, what's the probability of a breakdown? If I give this patient this drug at this dose, what does the simulation predict will happen to their cardiac output? And then, critically, the insights flow back. Engineers act on the predictions. They replace the bearing before it fails. The doctor chooses a different treatment protocol. The physical system improves, and the twin learns from that improvement, becoming ever more accurate over time. It's a perpetual optimization machine, a closed loop between the physical and digital worlds. Now let's see what this looks like in practice across the industries being most dramatically transformed. Aerospace was the industry that invented this concept, and it remains the most advanced practitioner. Airbus now builds every aircraft twice, first completely in the digital world, then in physical reality. Engineers simulate thousands of flight hours, stress tests, extreme temperatures, and failure modes before a single physical component is manufactured. The results are measurable. Digital twin adoption has accelerated aerospace prototyping cycles by 15 to 20%. Boeing and Lockheed Martin use digital twins to predict exactly when components on specific aircraft will need attention, not because a maintenance calendar says 6 months, but because the predictive model says this specific part on this specific aircraft is going to develop a fatigue fracture in 47 days. That is not maintenance scheduling. That is prophecy backed by physics. Manufacturing is undergoing an equally profound transformation. Siemens and General Electric now run entire factory floors as digital twins. Every machine, every robotic arm, every conveyor monitored simultaneously in real time. A vibration sensor on a motor picks up a signature. The AI recognizes it as the early-stage pattern of bearing degradation, a pattern it's learned from thousands of previous failures across thousands of facilities. It flags the machine, estimates the failure window, and generates a work order automatically, 72 hours in advance. A technician replaces a $40 bearing before it destroys a $400,000 machine. Across thousands of facilities worldwide, this scenario plays out millions of times per year. Digital twins are enabling manufacturers to reduce unplanned downtime by up to 25%. In industries where a single unplanned production halt can cost hundreds of thousands of dollars per hour, that is transformative. Now for the digital twin application that genuinely stopped me in my tracks while researching this video. In hospitals and research centers around the world, scientists are building digital twins of individual human patients. Not generic anatomical models, not average person simulations, your specific model, built from your genetic data, your medical imaging, your real-time vital signs, your entire medical history, integrated into a single, living, continuously updated computational representation of your unique biology. In cardiology, a virtual heart can be built that replicates the exact geometry, the specific muscle tissue properties, the hemodynamic quirks of one specific patient's heart. Cardiologists can then simulate what happens if we implant this specific valve prosthesis. What if we ablate this pathway? What if we adjust the drug regimen? All of this happens in the computer. The patient experiences none of the risk of physical trial and error. In oncology, researchers are building tumor digital twins, computational models of a patient's specific cancer, incorporating its genetic mutations, its metabolic behavior, its microenvironment. Doctors can then simulate different chemotherapy combinations, different radiation protocols, different immunotherapy approaches, and identify the treatment strategy most likely to work for that specific tumor in that specific patient. Not the treatment that works for most people with this cancer type, the treatment designed for you. This is not science fiction. It is happening in research hospitals right now. It represents the beginning of something medicine has aspired to for decades: genuinely personalized care. Treatment based not on population statistics, but on the digital copy of you. Cities are the most complex machines humanity has ever built. Millions of people, thousands of interdependent systems, water, power, traffic, air quality, emergency response, all interacting simultaneously in ways that are almost impossible to model with traditional tools. For most of history, urban planning was a combination of engineering, intuition, and expensive trial and error. Singapore decided there was a better way. They built Virtual Singapore, a comprehensive, real-time, three-dimensional model of the entire nation. Every building, every road, every underground utility, every live sensor feed. Urban planners can propose a new subway line and simulate its impact on traffic, energy, and pedestrian flow before a single meter of tunnel is excavated. Emergency services can run full disaster response simulations. Engineers can identify inefficient buildings and propose retrofits, all inside the model, at effectively zero cost. And Singapore is just one city. The European Union has launched Destination Earth, an initiative to build a full digital twin of our entire planet, the complete Earth system, atmosphere, oceans, ice caps, ecosystems, a scientific instrument of unprecedented scale, capable of simulating the effects of climate policy decisions decades into the future before those decisions are actually made. But we'd be doing you a disservice if we only showed you the highlights. Digital twins face real hard challenges. The first is data volume. A single modern commercial jet engine generates roughly a terabyte of sensor data per flight. Scaling this to entire cities or an entire planet requires computational infrastructure of staggering proportions. The second is cybersecurity. A detailed digital twin of a city's power grid, by definition, is a comprehensive map of how to attack that power grid. The cybersecurity demands of large-scale digital twin infrastructure are extraordinary, and the field is racing to catch up with adoption rates. And the third challenge is trust. When an AI model says replace this part in 47 days, how confident are you that the model is right? Validating these systems, proving their predictions are reliable across scenarios they've never seen before, remains one of the hardest unsolved problems in the entire field. These are not insurmountable, but they are real, and knowing them makes the successes we've described even more impressive. Here's what the next decade looks like. Generative AI is being integrated directly into digital twin platforms, meaning models won't just simulate known scenarios, they'll imagine new ones. An AI co-pilot that doesn't wait for an engineer to ask a question, but proactively surfaces insights. Based on the pattern I've observed over the last 72 hours, here are 3 scenarios you haven't considered yet, ranked by probability of occurrence. Self-optimizing factories that require no human operator to run experiments. City infrastructure that rebalances itself in real time as demand patterns shift, not because a human engineer decided to intervene, but because the digital twin detected the imbalance and executed the correction autonomously. Personalized medicine twins that update every time you receive a new test result, continuously refining their predictions across your entire lifetime. And at the largest scale of all, by 2030, we may have a living, operational digital twin of Earth's complete climate system, a scientific instrument accessible to researchers on every continent, a tool that can show, not merely tell, what happens to sea levels if global emissions peak in 2027 versus 2031, what happens to the Amazon basin if reforestation programs scale by a factor of 10, what 3 specific climate policy scenarios each produce, compared simultaneously in a single afternoon simulation run. We are quite literally building a digital Earth. Digital twins began as engineering tools. They've grown into something far more consequential, a new way for humanity to understand, optimize, and ultimately protect the physical world by first mastering its digital reflection. The copy is no longer a pale imitation of reality. In many ways, it's becoming smarter than the original. If this video gave you a new way to see the relationship between the physical and digital world, hit that subscribe button, because this is exactly what Cipher Sci is here to explore. Next week, we're going even deeper into the technology stack that makes digital twins possible. The sensors, the AI models, the edge computing infrastructure, and the data pipelines. Because understanding the concept is one thing, understanding how it actually works under the hood is something entirely different. I'll see you then.